we are going to talk about electrolysis. This is the process of decomposing an electrolyte by passing an electric current through it. The setup that we had for molten or aqueous substances is repeated here. Molten and aqueous substances that conduct electricity usually have charges or charged ions. Some of the charged ions are positively charged while others are negatively charged. And remember, positively charged ions are known as cations, while negatively charged ions are known as anions. Before we close the circuit, the positive and negative ions are randomly distributed across the electrolyte. If the electrolyte is molten, will require heating. If it is not, then it won't require heating. However, let us assume that this electrolyte is molten, so it will require heat. The electrons in this circuit are randomly arranged, but when we close the circuit, the battery will provide the driving force that will move the electrons in one direction. Now, when the circuit is closed, the dry cells provide the driving force to move the electrons in one direction. When the electrons move in one direction, the electrolyte will have some changes, which we call decomposition of the electrolyte. In this case, the electrons will enter the electrolyte through the cathode and leave the electrolyte through the anode. However, the positively charged ions in the electrolyte will be attracted to the cathode. As you can see, the direction of positively charged ions moves towards the cathode, while the negatively charged ions move towards the anode. Let us make this practical by looking into the electrolysis of molten lead to bromide. Molten lead to bromide is an example of a binary electrolyte. A binary electrolyte means an electrolyte that contains only one type of cation and one type of anion. Solid lead to bromide does not conduct electricity because the ions in solid lead to bromide are fixed and cannot move from one place to another. However, on heating to above 390 degrees Celsius, lead to bromide melts into a molten state. The ions of lead and bromine will become free and move randomly about the electrolyte. In this case, the electrodes that are used are graphite electrodes. Graphite is a suitable substance to use as an electrode because it is inert and does not react with most electrolytes. Additionally, it is a good conductor of electricity and it is relatively cheap compared to other electrodes such as platinum, which is very expensive, although it is the best. Upon closing the circuit, the bulb will light because molten lead to bromide conducts electricity. Another interesting thing that will happen is that the flow of electrons will move in one direction from the negative terminal of the battery to the towards the positive terminal of the battery or the dry cells. Interestingly, at molecular level, the lead-2 ions will be attracted towards the cathode since they are positively charged, and the bromide ions will be attracted towards the anode since they are negatively charged. From the law of nature, you know that negative charges attract. So negatively charged bromide ions are attracted towards the positively charged positive terminal of the battery, which is connected to the electrolyte by the anode. Once the circuit is closed, interesting observations start to be made. First, it is easy to notice the red-brown fumes at the anode. These are red-brown fumes of bromine vapor. At the cathode, a gray bead of lead metal is formed. From our previous class, we learned that the positively charged lead-2 ions are attracted towards the cathode, and once they get to the cathode, they pick up 2 electrons and form lead metal. In a similar way, bromide ions move towards the anode, and once they get to the anode, they gain an electron to form bromine, and then 2 atoms of bromine combine to form what we call bromine molecule, and that is what we see as bromine vapor. Chemically, these changes can be represented by electrode equations as follows. Two ions of bromine lose 2 electrons to form bromine vapor. Similarly, lead ions gain 2 electrons to form lead metal. This lead metal is the gray bead, while these bromine molecules are the brown vapor. Interestingly, look at the equations carefully and notice that the ions are written in liquid state because it is a molten lead to bromide. Similarly, the equation at the anode is written in an interesting way, since bromine ions lose electrons to form bromine molecules, which are bromine vapors. We would have written the equation as follows. However, In chemical equations, we do not usually use the negative sign. And that is why, just like in mathematical equations, we take these two electrons to the other side of the equation and they become positive. And that is why our equation at the anode is written in this form. Different binary electrolytes may be used in place of lead to bromide. For example, molten lead to iodide will form iodine gas or iodine vapors at the anode, that is represented by this equation. These vapors are identified as purple vapors, while at the cathode will form a gray bead of lead metal. Next, molten lead 2 chloride at the anode will observe a green-yellow gas, that is chlorine gas, while at the anode we'll observe a brown metal or brown bead, which is copper metal. For aluminium oxide, we'll observe a colorless gas, which is oxygen, at the anode, and a gray bead or gray solid at the cathode. For zinc chloride, we'll observe a green-yellow gas at the anode and a gray bead of zinc metal at the cathode.